Okay, welcome back. In this video, we're going to be talking about the concept of gravitational potential energy. So, we want to know how we can calculate the gravitational potential energy between two or more objects. And the hint is that it's not just mgh anymore. So, we'll start with our definition. And we want to remember that work is the integral of f dx. And so when we apply this to the force of gravity, we get something that looks like this. We'll walk you through this. First of all, the work done by gravity is the integral of the force from r1 to r2 of Fr dr. Okay? Now, Fr is the force of gravity, and it's g times the mass of the Earth times another mass over r squared. Okay, now we're using the mass of the Earth because we're talking about potential energy specifically between the Earth and another particle. Okay, so we have this negative gmm over r squared, and then we integrate that from r1 to r2. Okay, so we're going to get a negative sign out of it when we integrate, because the integral of 1 over r squared dr is negative 1 over r. Okay, and then we can see here that we have gmm over r, r2, minus gmm over r1. And in chapter 7, we said that the work done by gravity is equal to the negative change in potential, which is u1, which is this guy, minus u2, which is this guy. So that means that potential energy between two particles with mass can be defined as negative g, mass of the Earth, mass of the particle, over r. So there's something very strange about this 1 over r equation that we'll explore. First of all, let's just say that this work is path independent. Okay? Gravity is a conservative force. Okay? So F gravity is conservative. So that means that the work done along any path from r1 to r2 will be the same. Okay, so we can go on a straight line path from r1 directly up to r2, or we can go on a curve. And the thing to keep in mind is that any time we're moving perpendicular to the force of gravity, there's no work being done. So if I take this path and just look at one piece of it, when I go sideways like this, I have a force of gravity that is going down, but I have a displacement that's going sideways. And remember that work is F dot d, so it's times the cosine of the angle. So when it's 90 degrees, I have 0 work when F is perpendicular to d. Okay, that means that only this part of the path, the upwards part, is going to contribute. Okay, and no matter what path I take, as long as I go from r1 to r2, it can be shown that it's always going to have that same upwards path. Now, the other thing that's weird about gravitational potential energy is that we sort of think of a gravitational potential energy as, positive mgh. And this is where h is equal to 0 at Earth's surface. That's what we did back in our energy unit. But now what we're saying is that this is wrong, and actually h is equal to 0 at the edge of the universe. Okay? Well, but really, if that's a height of 0, maybe it's better to say that when we're at the edge of the universe, r, or how far we are away from the center of the Earth, is actually infinity. So that means that u of infinity is equal to 0, and that's because u is equal to negative g, mass of the Earth, mass of the object, over r. Okay? So that's this equation right here. And this potential energy is always negative, but it's becoming less negative as r gets greater. So r is measured from the surface of the Earth to the astronaut, and it's negative, okay? We have a negative value for u. Now things are a little bit different when we go inside of the Earth, and we're going to talk about that in just a moment. But like we said, as r goes to infinity, u goes to 0. Okay, so we're actually going to show that this expression, gmmr over r2 minus gmm over r1 is equal to mgh. Okay? And we're going to do this when h is equal to r1 minus r2, which is not so large. So we're talking about close to the center of the Earth. So first of all, we'll just write this out. Gmem over r2 minus gmem over r1. And we're just going to write this as gmem r1 minus gmem r2 over r2 r1. Okay? Now, we can actually factor that out. So we can write gmem over r1 r2 times r1 minus r2. And r1 minus r2 is h. Okay? So we're going to pull out an m, and then we're going to write g mass of the Earth over r1 r2. And then we're going to have r1 minus r2. And there's a couple of interesting things that we can do here. First of all, as we mentioned, r1 minus r2 is h. Okay? But close to the surface of the Earth, r1 is about the same as r2 is about the same as the radius of the Earth. So we could say that this term right here is about the same as big G mass of the Earth over radius of the Earth squared. And we know what that is. That's little g. And so now we have our final answer of mgh. Okay? So I'm doing some approximations, and mathematically this may not be 100% sound, but it at least gives you an idea of what's going on. Okay, so next time we're going to talk about satellite motion and energy and Kepler's laws.